BFN 122, Study Session 1, Factorial Notation and Binomial Expansion. Introduction. Factorial of a number n is the product of the first n natural numbers. Alternatively, this definition can be written as, factorial of a number is the product of all numbers from 1 to that number. Consider n as any natural number, then, the first n natural numbers are the natural numbers from 1 to the number n. The product of the first n natural numbers is the product of every number from 1 to the number n. The factorial of n is the product of every number from 1 to n. Binomial expansion is used in statistics to calculate the binomial distribution. This allows statisticians to determine the probability of a given number of favorable outcomes in a repeated number of trials. Binomial expansion is also interesting from a mathematical point of view. It gives mathematicians insight into the properties of polynomials. Factorial notation. There are many areas of mathematics and statistics where we come across the product of many factors like 2 by 1, 3 by 2 by 1, 4 by 3 by 2 by 1, etc. To remove the drudgery, a rather shorthand notation has been provided, called factorial notation. For any n factorial, denoted by n, is the product of the first n natural numbers. For example, 6 equals 1 by 2 by 3 by 4 by 5 by 6 equals 720. This is however usually written in the form 6 by 5 by 4 by 3 by 2 by 1. Binomial expansion. You are already familiar with the concept of polynomials. You, however, also have monomials and binomial algebraic expressions that have two terms, joined together by either a plus or a minus sign. For example, etc. Many times, we are faced with the problem of expanding binomial expressions. Summary of Study Session 1. In Study Session 1, please note the following. 1. There are many areas of mathematics and statistics where we come across the product of many factors like 2 by 1, 3 by 2 by 1, 4 by 3 by 2 by 1, etc. To remove the drudgery, a rather shorthand notation has been provided, called factorial notation. 2. For any n factorial, denoted by n, is the product of the first n natural numbers. 3. Monomials and binomial algebraic expressions that have two terms, joined together by either a plus or a minus sign. Study Session 2, Permutations and Combinations. Introduction. There are counting problems that come under the branch of mathematics called combinatorics. Suppose you are painting your house. If a particular shade or color is not available, you may be able to create it by mixing different colors and shades. While creating new colors this way, the order of mixing is not important. It is the combination of choice of colors that determine the new colors, but not the order of mixing. Permutations and combinations. Permutations and combinations, which deal with arrangements and selections, are two very useful concepts in mathematics, and thus have applications in a very wide range of real-life problems. You should assume that a production process involves a sequence of two processes, A and B. If it can be done in two different ways and B in three different ways, it may be interesting to know the number of different ways this job can be done. Notice that for any of the methods, ways, 1.1 and 1.2 of achieving A, there correspond to three ways of achieving B, i.e. 2.1, 2.2, and 2.3. This means that there are altogether 2 by 3 different ways of completing the production process. General principle of counting. If there are a sequence of n different operation and operation 1 can be done in m1 ways, operations 2 in m2 ways, operation 3 in m3 ways, operation n in mn ways, then there are a total of m1, xm2 xm3 x, mn ways of completing the total task. Combinations. Consider a group of 4 persons, say Adamu, Bola, Chindu, and Diprai. In how many ways can we choose, select, a committee of, A, 3 people and, B, 2 persons? Solution. A. The 3-man committee may be Adamu, Bola and Chinedu. Adamu, Bola, and Diprai. Bola, Chinedu and Diprai, or Adamu, Chinedu, and Diprai, e 4 ways. B. A 2-man committee can be any of the following: Adamu and Bola, Adamu and Chinedu. Adamu and Diprai, Bola and Chinedu. Bola and Diprai, and Chinedu and Diprai, i.e. 6 ways. Note that arrangement is not of any significance in this case. For instance, a committee of Chinedu and Diprai is the same as that of Diprai and Chinedu. This is called a combination. Summary of Study Session 2. In Study Session 2, please note the following. 1. Permutations and combinations, which deal with arrangements and selections, are two very useful concepts in mathematics, and thus have applications in a very wide range of real-life problems. 2. For any of the methods, ways, 1.1 and 1.2 of achieving A, there correspond to 3 ways of achieving B, i.e. 2.1, 2.2, and 2.3. This means that there are altogether 2 by 3 different ways of completing the production process. 3. If there are a sequence of n different operation and operation 1 can be done in m1 ways, operations 2 in m2 ways, operation 3 in m3 ways, operation n in mn ways, then there are a total of m1, xm2 xm3 x mn ways of completing the total task. Study Session 3. Sequences and Series. Introduction. Saying that a collection of objects is listed in sequence means that the collection is ordered so that it has a first member, a second member, a third member, and so on. Below are 2 examples of sequences of numbers. The numbers in the sequences are called Sequence 1. 3, 6, 9, 12, 15. Sequence 2. 3, 6, 9, 12, 15. You can also think of n as a function whose domain is a set of consecutive integers. Sequence. A sequence is a set of numbers, events, actions, etc. that occur according to a definite pattern. In mathematics, we are concerned about number sequences. These are sets of numbers arranged according to a definite order. The sets of numbers A, 2, 4, 6, 8, and B, 2, minus 2, 4, minus 4, 6, are examples of sequences. The numbers have not been exhausted. We have some types of sequences like arithmetic sequence or arithmetic progression, AP, geometric progression, GP, harmonic progressions, Fibonacci sequence, etc. Only the first 2 types will be considered with some detail in this work. Arithmetic progression, AP. Consider the following sequences: A, 2.4.6.8, B, 6, 9, 12, 15, and C, 77, 70, 63, 56. In A, the next term will be 10, that is by adding 2 to the preceding term, 8. In B, the next term is 18, which is got by adding 3 to 15. Finally, in C, the next term is 49, which is equal to 56 plus, minus 7, equals 56 minus 7. Notice that in each of these sequences, the difference between subsequent terms in each sequence is fixed or constant. This difference is therefore called common difference, D. The common differences in the sequences, A, B, and C, are obtained thus. A, D equals 8 s 6 equals 6 to 4 equals 4 to 2 equals 2. B, D equals 15 to 12 equals 12 to 9 equals 9 to 6 equals 3. C, D equals 56 to 63 equals 63 to 70 equals 70 minus 77 equals minus 7. Conventionally, you should regard the first term of a sequence as A. We already know that the common difference of an AP is D. But the subsequent terms are obtained by adding D to the preceding terms. It follows that the general AP will be of the form A plus D, A plus D plus D, A plus D plus D plus D, A plus D, A plus 2D, A plus 3D, which are the first 4 terms. Observe that first term equals A, second term equals A plus D, third term equals A comma plus 2D, fourth term equals A plus 3D, sixth term equals A plus 5D, equals A plus into bracket, 6 to 1D, nth term equals A plus into bracket, n, 1D. Given that the nth term of an AP is Dn equals A plus into bracket, n, 1D. Now put together, what are the total salaries receivable in the 2 offers within the first 10 years? This will lead us to a series. Series. By series, we mean the sum of the first n terms of a sequence, i.e. T1 plus T2 plus T3 plus Dn. Recall that Dn equals A plus into bracket, n minus 1D, whereas the first term in D is a common difference. To find the sum, S, of the first n terms we have S equals A plus into bracket, A plus D plus, into bracket, A, 2D plus, A plus, into bracket, N plus 3D plus A plus, into bracket, N, 2D plus, A plus, into bracket, N, 1DS equals A plus into bracket, N plus 1D plus A plus into bracket, N, 3D plus A plus into bracket, N, 3D plus, into bracket, a plus 2d plus into bracket, a plus d plus a. 2s equals 2a plus, into bracket, n. 1d plus 2a into bracket, n. 1d plus 2a, into bracket, n. 1d dot dot plus 2a plus into bracket, n. 1d plus 2a plus into bracket, n plus 1d2s equals n 2a plus, into bracket, n. 1d. Verification. Notice that the sequence could be extended up to the fifth terms, thus 3, 6, 9, 12, 15. S5 equals 3 plus 6 plus 9 plus 12 plus 15 equals 45. Arithmetic mean. Consider the AP, 2, 4, 6, 8, 10, 12. The arithmetic mean of the two numbers 6 and 10 is 8, i.e. into bracket, 6 plus 10/2 equals 8. Also, that between 4 and 8 is 6, being 4 plus 8/2. The arithmetic mean between three consecutive numbers of an AP, say A, B and C, and deduced is, the following way: common difference, C, B equals B, A plus C equals 2B. B equals into bracket, A plus B/2. However, the arithmetic mean of an n number of the elements of a sequence, say A1, A2, A3, n. Summation notation. Summation notation, which uses the sigma symbol, helps us to state series more compactly. For example, this series, A1 plus A2 plus A3, can be stated simply as S is called the summation index. This implies the addition of the various I, with I, an integer, assuming all the values 1, 2, 3, n. It starts with I equals 1 and terminates at I equals n. Alternating series. Sometimes, the signs on the series alternate. For example, 2 plus 4 plus 6 to 8 plus L0 is an alternating series and can be represented by recursion formula. Here, each term of a sequence is defined in terms of one or more preceding terms. Example, and can be defined as follows. A1 equals 0, A2 equals 1, and equals n1 plus n2. In the above example, the first two term is specified as 0 and 1, then subsequent terms are obtained by adding the two previous terms. Thus the above sequence is given as 0, 1, 1, 2, 3, 5, 8. This sequencer is called the Fibonacci sequence. Summary of Study Session 3. In Study Session 3, please note the following. 1. A sequence is a set of numbers, events, actions, etc. that occur according to a definite pattern. In mathematics, we are concerned about number sequences. These are sets of numbers arranged according to a definite order. 2. By series, we mean the sum of the first n terms of a sequence, i.e. t1 plus t2 plus t3 plus tn. 3. Summation notation, which uses the sigma symbol, help us to state series more compactly. 4. Sometimes, the signs on the series alternate. For example, 2 plus 4 plus 6 to 8 plus L0 is an alternating series and can be represented by Study Session 4, Ratios, Rates, and Proportions. Introduction. You and every other person experience ratios all the time. You read speed limit signs on the way to school, you hear commercials claiming that 9 out of 10 dentists prefer a particular type of toothpaste, and also figure out how much money you will make working over the weekend. You just don't call these values ratios. Make that connection, use lots of examples and problems to show how ordinary and everyday ratios are, and you will be more interested and comfortable in working with them. Ratios. A ratio is simply a comparison between two or more quantities of the same kind. For example, ABC NIG Limited has 15 females and 20 males on our payroll. The ratio of females to males is thus 3 to 4, written as 3 to 4. Note that the order is not arbitrary, 3:4, 4:3. The ratio of males to females is 4:3. Ratios are usually expressed in their simplest forms. To simplify a ratio, just multiply or divide by the same number. Recall that our ratio of females to males above was 15 to 20, i.e. 15:20. We divided through by 5 to obtain a 4:3. Rates. The rate could mean a fixed ratio between two things. It could also mean a quantity, amount, or degree of something measured per unit of something else. For example, 70 km per hour is a rate. N5 per 1000 is also a rate. Proportion. The proportion could mean a statement of equality between two ratios in which the first of the four terms is divided by the fourth. E.g. S/4 equals 10/8. S equals 10/8 x 4 equals 40/8 equals 5. We have direct proportion, inverse proportion, and indirect proportion or partial variable. Direct. dP, read as T is directly proportional to P or T varies directly as P. D equals Kp where K is constant. Example. The cost of bread varies directly as its number. When number equals 4, costs 600. How much would 71 halves loaves cost? Cn. C equals not where K is constant. When C equals 600. N equals 4. 600 equals 4K. K equals 150. 71 halves loaves will cost 71 halves x 150 equals 1125. Inverse proportion. A 1/x, read as A varies inversely as x. B equals kx, where k is constant. Example. The production capacity of a man varies inversely as his age. When Atata was 40 years, output per day equals 50 units. What will be his output at 80 years? Let C equals capacity and A equals age. C1/A. C equals Ka, where K is constant. When C equals 50, A equals 40. 50 equals K/40. K equals 50 x 40 equals 2000. When A equals 80 years. C equals Ka equals 2000/A. Equals 2080 equals 25. Indirect proportion. This is partly constant and then varies either directly or inversely. Break-even analysis. Profit is the most important goal of every business. The higher the profit, the greater the joy of the investor and the more he is considered successful. Profit is simply the excess of revenue over cost. This implies that revenue greater than cost equals profit, revenue less than cost equals loss. But revenue equals cost is break-even. Revenue, R, equals quantity demanded, Q, or purchased multiplied by unit price, P, i.e. R equals PQ. Cost on the other hand can be separated into fixed cost like a plant, vehicles, installation, and overhead and variable cost which depends on the units of products involved. You should notice that in making plantain chips, for instance, the machines, fryers, and manager's salary will be fixed, no matter how many we make, but the number of units of plantain chips will for instance determine the of packets that will be bought, thus the cost of packets becomes a variable cost. Many times we will be interested in knowing how many units of goods that must be sold to break even. Example. Okoro and Sons Nig. Limited produces hymn books. One-time fixed costs for a particular hymn book are 240,000. This includes such costs as typing, filming, plate, and overhead. Variable costs amount to 62 per unit of the hymn book. Again, this includes manufacturing, distribution, etc. If all the hymn books produced are actually sold at 87 per copy, how many must be sold for the company to break even? Solution. Let Q equals number of copies of hymn books sold. C equals cost of producing X copies of hymn books. R equals revenue. Break even is R equals C. But R equals units selling price X number sold equals 87Q. Cost equals fixed cost plus unit variable cost XQ. Equals 240,000 plus 62Q. Break even. 87Q equals 240,000 plus 62Q. 25Q equals 240,000. Q equals 9,600. The company break even when she produces and sells 9,600 copies of the hymn books. Summary of Study Session 4. In Study Session 4, you have learned that 1. A ratio is simply a comparison between two or more quantities of the same kind. 2. Ratios are usually expressed in their simplest forms. To simplify a ratio, just multiply or divide by the same number. 3. Rate could mean a fixed ratio between two things. It could also mean a quantity, amount, or degree of something measured per unit of something else. 4. Proportion could mean a statement of equality between. Study Session 5, Matrices. Introduction. You need to know that we have many applications of science, business, and economics in which we are required to display or store data in an array of numbers. The array of numbers is ordered and consistent. In order for the meaning of each element to retain its consistency, we have to arrange them in m rows and n columns. In most cases a matrix is labeled with a capital letter while its entries or components are represented by small double-scripted letters, The first letter shows the row it occupies while the second letter shows the column it occupies. Matrices. A matrix is a grid-like array of elements. It can also be seen as a rectangular array of quantities or expressions in rows and columns that is treated as a single entity and manipulated according to particular rules. When we arrange a set of numbers in ordered and consistent rows and columns, we refer to it as a matrix. A good example is given below. A matrix is labeled A with the numbers as the components or the elements of the matrix. A matrix is an array of numbers and the numbers are said to be ordered because the position of each number is important. The matrix A depicted above has some numbers in a row and some numbers along the column. A matrix may be said to have M rows and N columns, often written as MXN matrix. This is read as M by N matrix. Vector algebra. The basic rules for addition, subtraction, and multiplication for ordinary real numbers also apply to vectors. The case of division does not follow the same rule, so we say it is not defined. Vector addition and subtraction. We can add two or more row vectors together if they are of the same dimension. We can also add two columns vectors together provided they are of the same dimension. We do not add a row vector and a column vector. Multiplication of vectors. When multiplying in vectors, we can multiply two vectors or multiply a vector and a scalar. A scalar is any real number such as 1, 0, -1, 2, 5, 20, which have magnitude but no directions. Their positions are not important. In multiplying a real number by an n-dimensional vector, we use the real number to multiply each of the elements in the vector. Some special matrices. Some matrices are considered to be special since they possess some special properties that are applied in matrix algebra or in getting solutions to problems in matrices. Some of them include square matrix. A square matrix is a matrix that has an equal number of rows and columns, where M equals n. A 2 by 2, 3 by 3, and 4 by 4 matrices are examples of square matrices. The diagonal matrix. This is a matrix in which the number of rows, M, is equal to the number of columns, n, square matrix, with all elements 0 except the elements along the main diagonal, from the top left-hand corner to the bottom right-hand corner. The zero matrix. This is a matrix in which all the elements are 0. We can denote it as 0. The identity matrix. This is a matrix in which the number of rows, M, is equal to the number of columns, n, square matrix, with the elements along the diagonal from the top left-hand corner to the bottom right-hand corner as 1s and every other elements are 0. It is a diagonal matrix with each of the elements along with its major diagonal equals 1, 1. Transpose of a matrix. For every M by N matrix A, we can obtain another matrix at transpose of A, in which the rows and the column of the matrix A are in exactly the reversed order. That is, the first row of matrix A becomes the first column of the matrix at, the second row of matrix A becomes the same column of the matrix at, and so on. The following example shows the transpose of some given matrix. Matrix algebra. We can carry out some algebraic operations such as addition, subtraction, and multiplication in matrices just like we did for row and column vectors. The rules for addition and subtraction are similar to that in ordinary numbers, provided matrices to be added or subtracted have the same dimensions both for the row as well as the column. Addition of matrices. In the addition of matrices, it is important for the two or more matrices to be added to have the same dimensions, that is, the number of rows and columns of each matrix is identical to each other. When this is established, their respective elements are added together. We say that matrix addition is an element-wise addition. Subtraction of matrix. The rules for the addition of matrix are the same for that of subtraction. In this case, we are looking for the difference when we remove the second from the first. The following example shows how we subtract one matrix from the other. Multiplication of matrices. The product of two matrices are said to be defined if and only if the number of columns in the first matrix, say B, is equal to the number of rows in the second matrix, say C. The matrices are said to be compatible for multiplication, otherwise, it cannot be multiplied. In the multiplication of matrices, the elements of the first row of a matrix B, the first matrix, are multiplied by the corresponding elements of the first column of the second matrix C. The product is summed and is placed in the first column of the resultant matrix, say D. Similarly, the elements of the second row of matrix B are multiplied by the corresponding element of the first column of matrix C. The product is summed and is placed in the second row first column of the resultant matrix, and so on. Determinants of a matrix. In every square matrix, number of rows equals the number of columns. There is a single value known as its determinant. The value may be positive, negative, or 0. The determinant is very important because it can be used in determining the solution of a system of linear equations. Cofactor and cofactor matrix. The cofactor of the I element, where I is its position along the row and j is its position along its column of a matrix A, is the product of the minor of the I element and minus 1I plus j. The cofactor is actually the minor multiplied by either plus 1 or minus 1. It shows that the sign plus v or v depends on the location of the I element. Adjoint matrix. When we find the transpose of a cofactor matrix, what we get is known as the adjoint matrix, say adjective A. If we take the cofactor matrix in example 15 above and obtain the transpose at, interchanging the row with the column, as studied in section. Inverse of a square matrix. Generally, the division is not defined for matrix algebra. The inverse of a matrix is, however, used in matrix algebra in the same way division is used in ordinary algebra. It is important to note that not all square matrices have an inverse. This is because the inverse of A's square matrix has an inverse, which is called a non-singular matrix. The determinant of a non-singular matrix is different from 0, it could be positive or negative but not 0. A matrix whose determinant is 0 is called a singular matrix. We will discuss one of the methods used for obtaining the inverse of a non-singular matrix. Matrix inverse, adjoint method. E can use the cofactor matrix we studied in section 1.8.0 in determining the inverse of a square matrix. In the adjoint method of finding an inverse of a matrix, we have to go through the manipulation of the cofactor of a matrix and the determinant of the matrix. We recall from section 1.10.0 that the adjoint matrix is the transpose of the cofactor matrix. Summary of study session 5. In study session 5, please note the following. 1. A matrix is a grid-like array of elements. It can also be seen as a rectangular array of quantities or expressions in rows and columns that is treated as a single entity and manipulated according to particular rules. 2. The basic rules for addition, subtraction, and multiplication for ordinary real numbers also apply to vectors. The case of division does not follow the same rule, so we say it is not defined. 3. We can add two or more row vectors together if they are of the same dimension. We can also add two columns vectors together provided they are of the same dimension. 4. When multiplying in vectors, we can multiply two vectors or multiply a vector and a scalar. A scalar is any real number such as 1, 0, minus 1, 2, 5, 20, which have magnitude but no directions. Their positions are not important. 5. Some matrices are considered to be special since they possess some special properties that are applied in matrix algebra or in getting solutions to problems in matrices. Study Session 6, Application of Matrices to Systems of Linear Equations. Introduction. It is quite hard to solve nonlinear systems of equations, while linear systems are quite easy to study. There are numerical techniques, which help to approximate nonlinear systems with linear ones in the hope that the solutions of the linear systems are close enough to the solutions of the nonlinear systems. We will focus our attention on linear systems. Matrices and matrix algebra. One important use of matrices and matrix algebra is the replacement of a system of linear equations by a single matrix equation. Linear equations and matrix inverse. We can easily obtain the solution to a matrix equation if we have found the inverse of the matrix. In the above heading, we found that a system of linear equations can be replaced by a single matrix equation given as X equals B. If we multiply both sides of the equation by the inverse of A, we obtain A1x equals A1b. 1x equals A1b. Which is x equals A1b. Since any matrix multiplied by a unit matrix will give the matrix itself. Therefore the solution x for the equation x equals b is given by x equals A1b. Integral calculus. You try to recall that under differential equation, given a function f(x), we found a new function, x, which is the derivative of the former function. In this study, we are interested in finding the original function f(x), given x. This process is called antidifferentiation or integration. In many real-life situations, x may actually be known, and we are required to find the original function, whose derivative is given by x. From elasticity, we can deduce price. We can also estimate future market shares from given share growth indices, and future sales can be forecasted from provision growth rates of sales. The integral of the function x is written as. We have two types of integration processes, indefinite integration and definite integration. Indefinite integrals. Consider the following functions and their derivatives. x equals x2 plus 4, x equals 2x. b, fx equals x2, x equals 2x. cf, x equals x2 to 3, x equals 2x. Now equals x2. In the process of finding integrals, the constant in the original function is actually unknown. This is simply because the derivative of the constant in the original function was taken as 0. Therefore, we must add some constants to the outcome of indefinite integration. Thus, where c is constant. Note: 2x is called the integrand, x2 the integral, and c the constant of integration. Methods of integration. There are so many integration techniques. But we shall consider only two methods, integration by substitution and integration by parts. Definite integrals. A very important advantage of integration is that it can be used to find the area under the graph of a function, between two values of x. To the area bounded at the top by the graph, at the bottom by the x-axis, and on both sides by the lines of x equals a and x equals b. Consumer surplus. One very useful application of definite integrals is consumer surplus. The term consumer surplus is often used in economics to describe the gains or savings that the consumers make, the difference between what they were willing to spend and what they eventually spend. Jones Ahechi may be willing to spend 10,000 naira to acquire his first smartphone. For a second smartphone, he certainly would be willing to spend only less than 10,000 naira, maybe 8,000 naira. To make him buy a third one, the seller must bring the price further down, maybe 3,000 naira or even less. This shows that price goes down with additional units acquired. But the actual price of products is determined by the forces of demand and supply. Usually, at equilibrium, the price may be P0 where quantity is Q0. In this case the actual amount that consumers spend on willing QO quantity is P0 Q0. Summary of Study Session 6. In Study Session 6, please note the following. 1. One important use of matrices and matrix algebra is the replacement of a system of linear equations by a single matrix equation. 2. We can easily obtain the solution to a matrix equation if we have found the inverse of the matrix. 3. Cramer's rule is an order method available for solving a system of linear equations. It requires the calculation of determinants for a given set of matrices. 4. You try to recall that under differential equation, given a function f(x), we found a new function, x, which is the derivative of the former function. 5. In the process of finding integrals, the constant in the original function is actually unknown. This is simply because the derivative of the constant in the original function was taken as 0. A very important advantage of integration is that it can be used to find the area under the graph of a function, between two values of x. Study Session 7, Linear Programming. Introduction. Linear programming is the process of taking various linear inequalities relating to some situation and finding the best value obtainable under those conditions. A typical example would be taking the limitations of materials and labor and then determining the best production levels for maximal profits under those conditions. In real life, linear programming is part of a very important area of mathematics called optimization techniques. This field of study, or at least the applied results of it, are used every day in the organization and allocation of resources. These real-life systems can have dozens or hundreds of variables or more. Linear programming. According to Brown and Ravel, 1978, linear programming is a technique for specifying how to use limited resources or capacities of a business to obtain a particular objective such as least cost, highest margin, or least time, when these resources have alternative uses. It is a technique that systematizes for certain conditions the process of selecting the most desirable course of action, thereby giving management information for making a more effective decision about the resources under its control. Hanna and Saber, 1973, noted that the mathematical definition of linear programming is the analysis of problems in which a linear function, called the objective function, of a number of variables is to be maximized or minimized when those variables are subject to a number of restraints in the form of linear inequalities and/or equalities. Successful applications of linear programming exist in the areas of military, industry, agriculture, transportation, economics, health systems, and even behavioral and social sciences. The usefulness of the technique is enhanced by the availability of highly efficient computer codes and programs. The linear programming model, because of its high computational efficiency, is also the basis for the development of solution algorithms of other, more complex, types of operations research, or models, including integer, nonlinear, and stochastic programming. However, the computations in linear programming, as in most OR models, are typically voluminous and tedious and hence require the use of computers in their computations. Taha, 2001. The General Linear Programming (LP) Model. Linear programming models are a class of mathematical models that can be used to tackle a set of problems whose variables are linearly related. It is an optimizing technique whose constraints or scarce resources have limits, which are known and fixed. As stated in Smith, 1973, if linear programming technique is used to aid planning, the basic aim is to obtain a better understanding of the system, and subsequently improve the decision-making process. Some basic assumptions and conditions necessary for its successful application are given below. 1. Additivity. This means that the controllable variables of the model must be additive in objective function as well in the constraints. 2. Divisibility. This means a value of a controllable variable can be a fraction, and not necessarily a whole number. 3. Deterministic. This means all model coefficients are known and hence constant in the period under consideration. 4. Proportionality, which means that the objective function and constraints must be linear. Survey of some available techniques. As earlier stated, the goal of linear programming is to find an optimal value of the linear objective function while the domain of the function is restricted by a given system of linear equations or inequalities. Thus the major concern is how to determine as quickly and easily as possible the optimal value and where it occurs. In the past, various methods have been proposed. Some of the methods include graphical method, simplex method, artificial variables methods, dual simplex method, and revised simplex method. The graphical method. As noted in Taha, 2001, the graphical method is practical when there are as few as two variables and serves to clarify some additional aspects of linear programming problems. This method in conjunction with the dual to the problem can handle any number of choice variables so long as there are only two constraints or any number of constraints as long as there are only two variables. This is an approach called the solution space method, where the optimal value occurs at the point of intersection of two constraints called the corner point feasible solution. In practical business and management applications, the graphical method is well suited to solving problems where the number of products is not more than two or where two major cost structures exist. This is quite typical of small manufacturing or business concern. Once the material, time, or labor limitations are known and can be stated in a linear form, the problems can easily be solved and optimum solution determined, with reference to the objective function. The simplex method. This method was basically developed by George B. Dantzig in 1947 as an improvement on the graphical method of solving linear programming problems. The simplex method rests on two concepts, feasibility and optimality. The search for the optimal solution starts from a basic feasible solution or program. As in the graphical method, we search only the extreme point solutions. The solution is tested for optimality and if it is optimal, the search is stopped. If the test of optimality shows that the current solution is not optimal, a new and better feasible solution is designed. The feasibility of the new solution is guaranteed by the mechanics of the simplex method, as is the fact that each successive solution is designed only if it is better than each of the previous solution. This iterative process is continued until an optimal solution has been obtained. Urim, 2007. The simplex method is based on the assumption that the optimal solution to a LP problem, if it exists, can always be found in one of the basic feasible solution. Thus, in the simplex method, the first step is always to obtain a basic feasible solution. This solution is then tested for optimality by examining the net effect on the linear objective function by introducing one of the non-basic variables to replace at least one of the current basic variables. If any improvement potential is noted, the replenishment is made always by introducing only one basic variable at a time. Artificial variable methods. These are variants of the simplex method and two versions exist, namely, the two-phase method and the Big M methods. Baitler, Phillips and Wild, 1979, The, 1979, Bazarak and Jarvis, 1977, and Edgar and Himmelblau, 1989, have discussed the solution of an LP problem from a non-feasible starting point utilizing the two-phase method. While Taha, 1976, Bazarak and Jarvis, 1977, and Himmelblau, 1989, have discussed the Big M method of solution. In the two-phase method, the computation is divided into two phases. The phase 1 aspect of the two-phase method involves minimizing the sum of the artificial variables to obtain a basic feasible solution or verifying that no feasible solution exists. If at minimum the artificial variables are zero, Then we delete the artificial variables from further consideration. If the solution obtained turns out to be optimal for the original problem, we terminate the process. Otherwise, we go to phase 2, which is simply a repetition of the simplex method. However, Edgar and Himmelblau, 1989, note that if the artificial variables, at O value, are found to be basic variables at the end of phase I calculation, it means that the original system of equations contains dependent equations. But Bazara and Jarvis, 1977, and Thie, 1979, noted that this means the system has no feasible solution. The two-phase method can be conveniently applied to both maximization and minimization LP problems. The dual simplex method. This method was developed by Lemke, 1954. His idea stemmed from the duality theorem of linear programming problems. The existence of the dual simplex method has led to the renaming of the simplex method as the standard or primal simplex method. The primal simplex method begins with a feasible solution and tries to attain optimality while retaining feasibility. The dual simplex method starts with an optimal solution and tries to restore feasibility while retaining optimality. This method is also widely used in maximization and minimization problems as well as problems involving mixed constraints. The revised simplex method. This method is a streamlined version of the primal simplex method. Although the method of transformation is that of elimination for both the simplex and the revised simplex. In the former, all the elements of the simplex tableau are transformed, while in the revised simplex, only the elements of the inverse matrix are transformed from one iteration to another until convergence is attained or unboundedness verified. Thus the round-off errors which would accumulate and become so significant to yield false results in the simplex method is drastically reduced in the revised simplex method, since it is only transforming the basis inverse, and also, that standard method is available for improving the accuracy of the basis inverse matrix. Ike Potokin, 1999. Hypothetical empirical example. As earlier stated, this study is principally about the application of linear programming models in the day-to-day planning and management of business organizations. The aim, therefore, of this section is to bring into focus the need to clearly recognize some potential LP problems, formulate such problems as LP models, and employ the proper computational techniques to solve mathematical aspects that tie together the elements and variables in the model. Furthermore, statistical tests using analysis of variance, INOVA, can also possibly be applied to test some pertinent hypotheses that would naturally aid operations researchers, and indeed management, in determining how statistically significant the results derived are. In addition, it is pertinent to note that many general management and business problems in the real world can quite easily be represented and solved as linear programming problems. For instance, most small and large-scale organizations have available data which indicates the precise amount of labor hours and material resources needed to produce a unit of their product or service. Summary of Study Session 7. In Study Session 7, please note the following. 1. According to Brown and Ravel, 1978, linear programming is a technique for specifying how to use limited resources or capacities of a business to obtain a particular objective, such as least cost, highest margin, or least time, when these resources have alternative uses. 2. Linear programming models are a class of mathematical models that can be used to tackle a set of problems whose variables are linearly related. It is an optimizing technique whose constraints or scarce resources have limits, which are known and fixed. 3. The goal of linear programming is to find an optimal value of the linear objective function while the domain of the function is restricted by a given system of linear equations or inequalities. 4. The graphical method is practical when there are as few as two variables and serves to clarify some additional aspects of linear programming problems. 5. The application of linear programming models in the day-to-day planning and management of business organizations. The aim, therefore, of this section is to bring into focus the need to clearly recognize some potential LP problems, formulate such problems as LP models, and employ the proper computational techniques to solve mathematical aspects that tie together the elements and variables in the model.